Okay.
And that's basically it.
Okay. Okay. So what we can do is quickly also let us understand a few things about pH. Okay.
Okay.
Okay. So so pH is something which sort of tells you whether it's acidic, basic, neutral. That's what it tries to tell you. Okay.
Mm-hmm.
Okay. Now you have to understand a few things over here. That actually pH came. How did the definition of pH come? You know how to derive Henderson-Hasselbach equation?
Yeah, pH is equal to pK plus
Ah,
concentration of H minus over concentration of
no.
HA. Sorry, A
No.
minus
A minus over HA,
over
right?
HA.
Okay. Okay.
Yeah.
Now, if you look at this, how did that come from? Where did that equation come from?
I don't know.
Okay, so you must understand that. Why don't you write down HA plus water? Write in your notebook.
Okay.
And
Yeah.
is in equilibrium with A minus
HA
plus
plus
H3O plus.
it's
HA
HA
plus
plus
water H2O is in equilibrium with H3O plus A minus. So that means the acid is this way. Now remember, this is a weak acid. HA, when we write a reversible equilibrium mean, it is a weak acid. It's only
Okay.
partially hydrolyzed. If it
Because
is a
it's not
strong,
stable
if it
fully.
is a strong acid, like suppose you
Yeah.
put HCl and water, only there will be forward direction arrow. There will be no reverse direction.
Yeah.
So strong acids, you can't write that kind of an equation because everything is completely converted. HCl becomes H plus Cl minus, right?
Okay.
Okay, so when we talk about pH, we are essentially talking about weak acids or weak bases.
Okay. Yeah.
Okay, so when you look at it, so HA plus water, because it is in water, it will form H3O plus A minus. Do you agree?
Mm-hmm.
Because H plus will go and bind with the lone para electrons on oxygen of water.
Yeah.
Okay, so now this is it. So if you write an equilibrium constant K, it will be concentration A minus multiplied by concentration of H3O plus divided by concentration of HA plus concentration of water. Did you write it down? In your
Yeah.
notebook?
Can you repeat that?
K is equal to equilibrium constant K is equal to concentration of A minus. That is A minus in brackets. Okay.
Yeah.
Multiplied by concentration of H3O plus. Okay. Divided by concentration of HA and concentration of water.
Yeah.
Okay. Then you keep writing the steps as it. So, since suppose there is 1 liter of water, what is the concentration of water in 1 liter of water?
Just 1 molarity.
Yeah, how much?
1 mole per liter.
Yeah, 1 more. No, how can it be 1 more? What is the molecular weight of water?
Let me get my calculator. It's 18.016.
Okay, so 18. So 18 grams is 1 mole, right? Now 1 liter means how many? What is the weight of water?
1000 grams.
1000 grams. So 1000 grams means number of moles of water in 1000 grams of water is how much?
55.5.
1000 divided by, so it is 50. So concentration of water is 55.54, isn't it? Okay. Now, if you look at this one, the acids are all weak acids and a very dilute one. So it might be 0.1 molar, 0.2 molar. So for all practical purposes, the concentration of water is constant. It doesn't change much.
Okay.
because number of water converted to H3O plus is so small.
So
Okay,
it's negligible because it's not changing.
not changing much. It does change.
Okay.
How much of water H plus is taken by water is a small amount relative to the 55.54 molar. It might be 0.01 molar or 0.001 molar.
Okay.
So this 55.54 also can be taken as part of the constant, the equilibrium constant multiplied by 55.54. So that is called Ka, dissociation of acid Ka. So Ka is equal to Ha, concentration Ha multiplied by concentration of A minus multiplied by concentration of H3O plus divided by concentration of Ha.
Yeah.
Okay, so that is Ka.
Yeah.
Okay. Now, if you say, now what you can do, you take negative logarithm on both sides. Minus log Ka is equal to minus log H3O plus into A minus upon Ha. Put logarithm.
Yeah, I see it now because then the log K would become PK.
Pk. Minus log Ka will become Pk, right?
And then log H3O plus will become PH.
And minus log this thing
A minus
HF.
over H.
So you can, what you can do is you can shift that one to the left where pK is there. So pH is equal to pKa plus log A minus upon Ha.
Yeah.
You understood now how this is derived?
Yeah.
Okay. So if you look at this particular one, so what you can see is that pH is defined for only dilute solutions. Okay.
Okay.
Okay. So you can do a lot of calculations based on that. Suppose you take acetic acid as an example.
Yeah.
So the pK of acetic acid is around 4.7. Around 4, you can put it at 4.7.
Yeah.
Okay. So now, since you know pKa, you can find out, and if suppose it is 0.01 molar, Ha, for example, so A minus will be some fraction, isn't it?
Yeah.
So you can literally calculate. So you will see that suppose A minus is equal to Ha.
Yeah.
Concentration of A minus is equal to concentration Ha. So log will become what?
So just log 10, 1.
No,
The 0.
1. Log 1 is 0. So
0.
pH is equal to pKa. Understood so far?
Right. And this is when the concentration
That means, no, now listen. So pK is defined as pH at which there is equal concentration of dissociated and undissociated form. That is Ha and A minus is equal concentration.
Yeah.
Okay, so we define always pK as the pH at which there is equal concentration of A minus and Ha.
Okay.
Okay, now this has a lot of importance. Now, so as you can see, the whole thing is around A minus upon Ha. But then if you look at the original equilibrium, Ha plus water going to H3O plus A minus. Okay. Suppose you were to put some small amount of acid there.
Yeah.
Okay. So what will happen if you put acid to the
The
equilibrium?
equilibrium shifts, right?
Shift to the left, isn't it? So there will be more of Ha.
But wouldn't the equilibrium shift right to the forward?
No. When you put H plus, it is
Oh, so
already
it will be
equilibrium.
H3 plus. It
So
will be for
H3O plus constant, so it will decrease. It will move towards the left.
Oh, okay. Okay.
So what happened? You have put an acid, but if you look at the pH would not have changed.
Oh.
So this is what we call as buffering. What is it? Buffering. So a buffer is one where you add some acid or alkali, doesn't cause a change in pH.
Right.
Okay. So the buffering is the one which gives that stability.
So it doesn't matter how much acid
Not
or
how
base
much,
you
up to a
add.
limit. For example, let us do a calculation.
Okay.
Suppose you had 0.001 molar acid, Ha.
Okay.
That is 10 raised to minus 3 molar Ha, right? So when you have 10 to the power minus 3 molar Ha, okay? So what will happen? What will be the concentration of H3O plus and A minus?
It would be equal.
No, it will be equal, right? But how much?
0.001.
Because you know the pKa, no? You know the Ka value.
Yeah, so
Because you know pKa, so you can calculate Ka. What is the Ka? Minus log of that one. What will be that value?
So 10 to the power of negative concentration.
And negative how much?
0.001.
Molar is there. So what happened?
I didn't understand your question because we don't have the Ka for this reaction.
You have, no? I give you pKa is 4.7. I gave you, no?
Oh, did you?
I have already given you pKa value. So you can calculate the Ka for that.
pK is equal to 4.7. Yeah, so 10
So
to the
Ka
power
will be
of negative 4.7, which is 1.995 times 10 to the power negative 5.
negative 5. So that is, so for every molecule, every 10 to the power 5 molecules going into water of the acid, it will produce 1 A minus.
Okay.
You understood?
Yeah.
Because that's what Ka means. Then how many will dissociate? So for every 10 to the power 5 minus 5 molecules, you have 1 molecule of A minus. So in 0.001 molar, how many molecules of Ha are there?
How many molecules?
Yeah, because 1 mole is 6.02 into 10 to the power 23.
Yeah.
So you can calculate how many molecules are there.
0.0001 times 6.
6.02 into 10 to the power 23. So
Yeah. $3,049. Would it be 3,050?
huh? How much?
3,050?
No. How can that be?
No,
You
wait.
have done some mistake somewhere.
But you said
I
0.00.
say every 10 to the power 5 molecules of Ha, you get 1 molecule of A minus, right?
Yes.
So if this many molecules are there of Ha, how many will be produced as A minus?
Oh, so it's the 10 to the power negative 5 times Avogadro's constant.
Yeah. So that will be something like 10 to the power 18 or something, right?
Oh, just a minute. No, it will be 60.8.
What 50.8?
60.8.
Into what?
Nothing.
What do you mean? See, when you multiply 6.02 into 10 to the power 23 by 10 raised to minus 5, right? 10,
Yeah. Wait, let me try it again. I typed it in wrong actually. Yeah, I got 18. 10 to
Huh?
the power negative 18.
18, isn't it? 10 to the
Yeah,
power 18 are there.
yeah.
So for every molecule, it only gives, every 10 to the power 5 molecules, it only gives one molecule of A minus, right? Dissociation constant.
Yes.
So 10 to the power 18 will give how many?
Um,
So 10 to the power 18 divided by 10 to the power 5, right? That is 10 to the power 18 minus 5. 10 to the
yeah.
power 13.
Oh, okay.
Is that clear?
No.
See, every 10 to the power 5 molecules of acid, when you dissolve it in water, you produce only one molecule of A minus, right?
How did you get that? Because Ka
You
is 10 to the power
Ka
negative 5.
Ka is 10 to the power
Negative 5.
negative 5, right? What
Yeah.
does that mean? That if there are 10 to the power 5 molecules of acid, you will only get one molecule of A minus.
Oh, okay.
Is that clear?
Okay.
What is 10 to the power 5? If you have one molecule, it only give you 10 to the power minus. That's not possible. So for convenience, I'm taking, there are 10 to the power 5 molecule. So how much A minus will be produced?
Okay.
So it will only produce one.
Yeah.
Is that clear to you? I'm just trying to make you understand what is involved.
Yeah. Yeah, I
We are
get it.
imagining, okay?
Mm-hmm.
So if you have that much 10 to the power, 0.001 molar acid, that you convert a number of molecules, which is something like 10 to the power 18 molecules, right?
Mm-hmm. Mm.
So if 10 to the power 5 molecules give you 1 of H, so how much will 10 to the power 18 give you? So
Which
10
is
to the
just
power
divided
18
by
divided,
5. Which will be divided by negative 5.
not negative 5. Now 10 to the power 5. No, we are talking about 10 to the power 5 molecules. So it will be divided by 10 to the power 5, no?
Okay.
So that will go in the numerators. It will be 18 minus 5.
Which is 10 to the power 30.
So it will only produce 10 to the power 13 molecules.
Yeah.
Okay. Now, if you want, you can divide it by 6.02 into 10 to the power 23. You will get the moles of A minus produced.
Mm.
Understood?
Yeah.
You can convert the number of molecules into moles by dividing it by 6.02 into 10 to the power 23.
Okay.
So that becomes 10 raised to minus 3 plus 10 to the power 13.
Right.
23 minus 13 is how much? 10. So it is 10 raised to minus 10.
Okay.
Are you
Yeah.
getting?
I'm a bit lost.
I've been trying to make you go through both the calculation, number of molecules and number of moles. Go through it step by step what I said.
Yeah, I'll try that. So
Yeah,
basically,
that's good.
Ka, which is the dissociation constant for acid, tells us how much of 1 mole of acid, but how many
A minus.
molecules of A minus HA produces.
Yes.
And we got 10 to the power negative 5 molecules of A minus.
Yes.
Or was that 10 to the power
That
negative 5 HA molecules give 1 molecule of A minus?
10 to the power 5 molecule produce 1 molecule HA, A minus. Correct. Correct.
Okay. And then we found out how many molecules of A minus there were. So we just multiply 10 to the power negative 5 by Avogadro's constant.
Yeah. So you get 10 to the power 18.
Yeah.
So
And
there are 10
then
to the power 18 molecule HA. So A minus will be 10 to the power 18 multiplied by 10 raised to minus 5, right?
Yeah, that makes sense.
See, you have to understand what is happening in solution. That's why I took you through this process. I could have done it through equation, but you will not appreciate.
Yeah. Yeah.
You understood now? So when Ka essentially tells how many A minus will be produced.
Mm.
Is that clear?
Yeah.
And remember, this is only for weak acids or weak bases.
Mm.
That you have to remember.
Okay.
Okay. So now, suppose you want to make a pH with this HA and A, how will you make? Let's say you want a pH of, say, 5.
Mm-hmm.
So how much of HA and how much of A minus will you use to make it pH 5?
So the number of hydrogen molecules would be
No,
10
no,
to the
wait.
power
So
negative.
first write the equation. pH is equal to pKa plus log A minus upon HA.
Mm-hmm.
Constant. Right?
Yeah.
Write that down.
Uh-huh.
Okay. Now write pH is equal to 5.
Okay.
And pK is 4.7.
Yeah.
Plus log upon A minus upon HA. Right?
Mm-hmm.
So log HA upon A minus is how much? 5 minus 4.7. That is 0.3.
Okay. Yeah.
So,
And then so 10
so
to the power
what,
negative 0.3.
yeah, so now A minus upon HA will be how much? Anti-log of that
0.5.
number.
0.5.
Anti-log of 0.3. Huh?
So 0.5.
How 0.5?
So it's 10
Anti-log
to
of
the power
0.3.
10 to the power
Anti-log of 0.3.
yeah. So 10 to the power negative 0.3,
Ah,
which is
okay.
0.5.
Okay, whatever value you got, right?
Mm-hmm.
So the ratio of HA and A minus should be in that ratio.
Yeah.
So you should know. So suppose it is like simple. Suppose there are, say there are 100 apples.
Mm-hmm.
Vishruti gets, say, 60 and I get 40.
Yeah.
So,
Mm-hmm.
okay. So what should be the ratio of distribution? 60 by 40, right?
Yeah.
That is
Lower.
3 by 2. 3 by 2.
Mm-hmm. Yeah.
So for every 3 apple Vishruti gets, Professor Kannan gets 2 apples.
Mm-hmm.
Similarly, in this, how much HA is required and how much A minus is required.
Yeah.
So HA is available in bottle. A is
Mm-hmm.
available as salt like sodium acetate or potassium acetate. You can calculate how many moles are required to produce, say, 0.001 molar of pH 5.
Okay. Yeah.
Did
Mm-hmm.
you understand?
Yeah.
I am only introducing to the concept. We have not done the problem, but this is how we will go about solving the problem.
Okay.
Okay.
Mm-hmm.
So this is very important. Now I also told you, if you remember, this equation is only valid for dilute solutions.
Yeah. Mm-hmm.
Suppose you had something like, say, 10 to the power minus 8 molar HCl.
Mm-hmm.
I mean, acetic, 10 to the power, say, in acids and all this, but if you were to calculate pH, it can be a very dilute. What happens in HCl and all that, when you have very concentrated, even though it is a strong acid,
Mm-hmm.
in concentrated solution, all the HA doesn't become A minus.
Right.
All the
Mm-hmm.
HCl doesn't become Cl minus in concentrated form.
Okay.
In
Okay.
dilute form, they do 100% dissociates.
Because of saturation?
No, not such a. There's a reason we'll come to it. So we always say we don't use the word concentration. We use a new word called activity.
Activity. Yeah.
It is like how many active H plus molecules are there.
Okay.
For example, in a class, there are, say, 100 students. How many students are attentively listening to the class teacher?
Mm.
That's
Yeah.
called activity.
Mm.
So activity is always defined as activity is equal to activity coefficient into concentration of the acid.
Okay.
Okay.
Yeah.
So when concentrated solutions come, those equations, 100% dissociation doesn't work. For example, say you are asked the question, what is the pH of 10 raised to minus 8 molar HCl?
Okay.
So what will be your answer mathematically?
Whatever the concentration was,
No,
the negative log 10
no.
of that concentration.
How much is it? 10
So
raised to minus 8 will be? Log of minus 10 raised to minus 8 will be?
10 to the power negative 8.
Yeah, how much?
8.
8. That means it's alkaline. So you come into a contradiction.
Why?
Because you have taken acid and it is showing alkaline pH. How is it possible?
Because the acid is dilute, very dilute.
No, acid is a concentrate, dilute, no doubt. But the point is now there is a H plus concentration coming from water molecule also, which we, in the earlier one, we said it doesn't contribute. In dilute, very dilute solution, water also contributes to H plus. So concentration acid is concentration of acid plus concentration of water. H plus coming from water.
So in very dilute acid, water also contributes to
the acid, H plus.
Okay.
So you will see that the pH will be around 6.8 or something. So you have to remember that in very dilute solution, very dilute solution, contribution of water, which you neglected earlier in your equilibrium, becomes important.
Right.
You understand? This you have to remember. Nobody will tell you this. These are all questions asked in exam.
Okay.
Have you understood? Because how can an acid become alkali?
Yeah, I get that. But how would you then you can't calculate the true value of pH from this?
No, you can.
Okay.
Because you know Ka of water.
Oh, okay.
10 to the power minus 14.
14.
Ka is 10 to the power minus 14. So from that you can calculate.
Okay.
Okay. So that's not difficult. You will do all those calculations later. But first understand the concept.
Yeah.
In concentrated ones, for example, say you have say 1 molar HCl. What is the pH? If you look at it, minus log H plus will be how much? Log 1. So pH will be 0.
Yes.
But you'll observe it is never 0. It is around 0.7, 0.8, something it will come. Because the active H plus present in the concentrated one is much less than what we theoretically calculate.
Okay.
You understand?
Yeah.
So that is what you have to understand. So just revise what we did. Just read out what you wrote so far, and then let us make a summary of it first.
Okay. Do I have to read it out loud?
Yeah. Read it out loud so that I know what you have written.
Okay.
How we started and go about. Because it's a concept I want you to understand.
So I just wrote the derivation first. So I wrote the equilibrium reaction HA plus H2O going into with a bidirectional arrow, H3O plus A minus. And then I wrote the Ka dissociation constant. H plus concentration of H plus times concentration of A minus over concentration of HA. And then I take the negative logarithm of both sides.
Correct.
And then it becomes log Ka becomes pKa, and log log H3O becomes pH. And then we just have negative log A minus over HA. And then I just rearrange for pH. So then it becomes pH is equal to pKa plus log A minus over HA.
Yes.
And then I wrote concentration of water is 55.54 molarity, which is negligible because it is not changing much.
Yeah.
And then I wrote pKa is equal to pH,
Mm.
at which there is an equal concentration of A minus and HA.
Mm.
And then it was just about activity, all of the calculations that we did. And then activity, which is how much active H plus molecules are there.
Correct.
And in very dilute solution, water also contributes to pH. That's what I wrote so far.
Very good. So now you got an idea, right? So this is a very basic thing to pH. So pH is very important. Like for example, say if you look at the pH of our blood,
6.7.
that is 6.7.
Yeah.
Okay. So what happened? Any change in that also will affect our physiology of our body.
Right.
That is why you take lemon juice, everything which is acidic, the pH of blood doesn't change.
Because there might be a buffer system in place.
There is a buffer system. Very good. And the buffer is it is H2. You can write down H2CO3, or let us write CO2. When it dissolves in water, it goes into bicarbonate. HCO3 minus.
Yeah.
Okay. Then further, that HCO3 minus picks up another H plus to form
H2CO3.
Carbonic acid is in equilibrium with CO2. So because our body produces carbon dioxide, it takes in oxygen and releases carbon dioxide.
Yeah.
So when carbon dioxide dissolves in water, it becomes carbonic acid. But the buffer is so good that it doesn't allow. So what happens? So H2CO3 is in equilibrium with water to produce HCO3 minus. Write down HCO3 minus plus H3O plus.
So okay.
Then HCO3 minus in equilibrium with water.
Wait just a minute.
Produces CO2 plus water. H3O plus H3O plus.
Wait. So CO2 plus H2O is in equilibrium with HCO3 minus. And this HCO3 minus, when it reacts with H3O plus or H2O?
I mean, H plus, whatever it is. So it has to form carbonic acid, H2CO3. See, basically what happened, the carbon dioxide reacts with water to produce bicarbonate, carbonic acid. These are all weak acids, so they are in equilibrium.
But my question is, shouldn't CO2 and H2O form bicarbonate, which is H2CO3?
Yeah, it does form.
Oh, because you said HCO3 minus.
No, that is one step. Then that HCO3 minus, when it reacts with this thing, will form H2CO3.
Okay.
So what happens is that when our body releases carbon dioxide, the equilibrium shifts. Because you have excess carbon dioxide, then it becomes carbonic acid. Then you find when oxygen is taken up, this equilibrium shift to the left. So that I'll teach the physiology of it later. Okay, so what happens is the bicarbonate is the buffer in our blood.
Yeah.
You understand? So our body maintains this by taking in oxygen and releasing carbon dioxide, which is removed out through the nose. So breathing in oxygen, giving out carbon dioxide.
Yeah.
So that the pH is maintained.
Yeah.
So this is the beauty of the physiology of the reaction.
Yes.
Are you able to understand?
Yes.
So this becomes very, very critical. So now let us look at, say, you made curd. You remember you made curd in one of the experiments, right? And you use what is called lactobacillus.
Okay. Yeah.
So that was releasing H plus. So So what is happening? So the pH of milk is going up from 7.4 to 7.27, 6 point like that. It goes up to 4.6.
Oh,
Okay.
Yeah.
So when lactobacillus tries to grow, there is also a buffering in milk.
Oh, okay.
It keeps on releasing it, and when it becomes 4.6, the casein precipitates or forms what is called curd.
Mm.
You understand? So
you
all this are
basically
pH changes.
So you've
Huh?
overwhelmed the buffer, and the buffer is not able to work anymore.
Yes.
Okay.
So that is why we say that you don't need lactobacillus. Take some lemon juice, which is an acid, and pour it. After some time, it will form curd.
Yeah.
You want to speed up. Or you can even put HCl and do it.
Yeah.
So pH keeps things in solution. Change of pH can bring it out of solution. You understand?
Yeah.
So that is why it is very important that the pH plays a very important role in our daily life. You understood?
Yeah.
That is why Henderson-Hasselbach equation is very, very important. Okay.
Yeah.
So whenever we do biological reaction, we do it in a buffer. So that any change happens, it doesn't affect the reaction.
Right.
So when you have enzyme, they work only at one particular pH. Okay. For example, your stomach is acidic.
Yes.
So there are acidic enzymes which work in the stomach. In the intestine, you have alkaline enzymes which work in alkaline condition.
Yeah.
So enzymes which we talk about are also very fussy about the pH to be active.
Yeah.
Okay. So that is something. So you have enzymes which act at different pHs.
Yeah.
Okay. So our body whole digestive system is based upon the enzymes which act at a particular pH. Okay. And because of the particular pH, molecules like protein and all have a specific charge. Number of positive charges on them is different. Number of negative charges on them are different.
Oh, why? Like, how does pH affect that?
Yes.
Okay.
Okay. And this has a lot of connotations in our understanding biochemistry. So in biochemistry, pH is a very important one. Okay. For example, some things get stabilized due to pH. For example, say you have an enzyme like say trypsin.
Yeah.
Or chymotrypsin, if you talk about. If you keep it in acid pH, they remain inactive. They are stable, but will not be reactive.
Oh.
But moment you bring it to alkaline pH, it will start acting.
Right.
So if you want to stabilize something, also pH is. For example, we talked about penicillin. When the original work was done on penicillin in the 40s, what they found was that normally penicillin is secreted by a Penicillium notatum, a fungus.
Okay.
So what happened, those days they used to extract organic compounds with organic solvents.
Right.
But they found that moment you extract it, slowly penicillin loses its activity. It loses it in a few days.
Because it has enzymes in it as well.
Not only enzyme, the structure itself is not stabilized. The penicillin molecule structure is not stabilized when it is an organic solvent. So somebody discovered that if you put it at pH 6.5 buffer, it suddenly becomes stable.
Oh. Okay.
And it becomes stable for 3 years.
Like, okay.
So that's how penicillin is available commercially. It is stable for 3 years. They manufacture large amount and supply it everywhere. Whenever somebody wants as a bacterial infection, take penicillin if it is acts on the penicillin.
Yeah.
So what I'm trying to say is that this buffering is a very important aspect.
Okay.
You understood?
Yeah.
So you will see buffering plays a big role in many things. Okay.
Yeah.
So similarly, if you look at our, the every country says we have so much of buffer stock. You heard of the word buffer stock in economics?
No.
For example, say we have enough wheat in our country that it will take care of it for the next 4-5 years. So what do they do? So they produce enough wheat,
Yeah.
which is kept stored. That is called buffer stock. Suppose that year, next year, there is no good crop of wheat, they're able to take that wheat and supply to people.
Okay. Yeah.
So this is called buffer stock. So this happened to India, that there was a time we did not have enough wheat to give it to people. You understand? We also went through a phase when there was not enough rice. Because our yields were very poor, we did not have enough buffer stock. Okay. Then we developed high yielding varieties. Now we are surplus in India. But in the 60s, I remember 66, 67 and now, we used to get, even in the hostel, when we were in the hostel, we used to get in the 70s, one small bowl of rice.
Yeah.
You can have any amount of wheat, chapatis. But we did not have rice that much. So we used to have rationing of rice.
Yeah.
So houses, you ask your mother and all, they may remember.
Okay.
So we didn't have enough buffer stock. We had to import from foreign countries to meet the rate. Just like petrol. We don't produce petrol, so we buy petrol.
Yes.
And our economy depends upon the cost of the petrol. That is why every country tries to maintain enough buffer stock. Same thing is happening in the rare earths, as you would have seen. America, why is it so keen to capture countries? Because they depend on China to get rare earth, and China dictates its own terms. So they said, okay, I'll take over Greenland, I will take over this place, I'll take from us. These are all happening because otherwise you become slave to some country.
Yeah.
So the buffering is a very important aspect, even in economics.
Yeah.
Are you getting what I'm trying to say?
Yes.
So kindly concentrate on this Henderson-Hasselbach contest. Next time I'll start doing problems on it for you.
Okay.
But you understood the concept, no? Or you want any revision on this?
No, I understand this.
Okay, that equilibrium is very important. And remember, it is for weak acids only.
Yes.
Henderson-Hasselbach equation applies. Okay. And for dilute solution, H plus contribution comes from water also.
Yeah.
Okay. So what I suggest, you make a notes on this, because I could have gone to the next one, but I want you to reflect on the whole thing, do your reading and make your own notes.
Yeah.
Because I've tried to give you that's why today I didn't show you any slide. I said I wanted you to develop the concept.
Yeah.
Okay.
Yes.
So you have any doubts, you ask me now.
Not of what we've learned today. I think I get it pretty well.
Huh?
I get what we've done today pretty well.
Yeah. So even in flowers, some of the flowers, the flower is light in color. But when sunlight falls on it, it becomes red. There are a lot of flowers which change color. That is also a pH changing phenomenon.
Okay.
Okay, so you have to remember that pH can create the color intensity also. So many times when you do color reactions, if you want to intensify, you put some acid or alkali and see how intense it becomes.
Okay.
So pH buffer, but the pH also can affect the color intensity.
Yeah.
So if you want to make it darker, you just have to change pH, the color will change. For example, when you will be doing titration with phenolphthalein, say acid alkali.
Yeah.
Have you done that titration?
We've not done the titration now.
Okay.
But
So
we've
what you
used
will see is at acid pH, phenolphthalein is colorless.
colorless.
But the moment you cross pH 8, it becomes pink in color.
Yeah.
Again, it's a pH phenomenon.
Mm.
So in a phenolphthalein colorless form going into, so it is a hydrogen ion effect, alkali effect. OH minus removes some H plus ion, which gives it the pink color.
Yeah, it's all the equilibrium and then the
Yeah.
equilibrium shifting and producing a species with that color.
Okay. So phenolphthalein is also, if you look at the structure of phenolphthalein, and when you put alkali, whatever, check in your internet. Phenolphthalein structure, and when you add alkali, what happens, it will tell you. Just have a look at it.
Phenolphthalein structure. I'll just share the screen.
So what do you see there? There is a lot of OH, if you can see.
Yeah.
Okay. So when you keep on adding alkali OH minus,
it will shift the equilibrium.
The OH will go into O minus. S plus, so H3O plus and O minus. That gives the pink color.
Okay.
So the dye is actually changing color. So you can have dyes changing color at various pHs. You can have this one changes at say 8. Okay.
Yeah.
There are some which will change at 7. Some will change at 6. So you can use for a particular change to find out what is the pH change. So there are specific dyes which will tell you the change instead of measuring.
Yeah.
So you put up a search on the net saying dyes for different measuring different pHs.
We did this in school. Methyl orange is for acids, bromothymol blue is for neutral solutions, and phenolphthalein is for alkaline solutions.
So just write it down. This is the one easy way to do it. So if you think it is acidic, put that dye, you will know immediately.
Yeah, we're supposed to know that because we'll have a titration practice done.
Okay. So now you understood the concept, no?
Yeah.
So all along, that is what is happening. Okay?
Yeah.
So I'm just taking you through this thing. So then you also see color of flowers and the pH. Just put that. See, soil pH directly influences the color of certain, most notably hydrangea microphylla by affecting the availability of aluminium ions in the soil. Acidic soil allows for aluminium absorption, producing blue flowers, while alkaline soil pH locks up aluminium, resulting in pink or red bloom.
Oh, so you can change the color depending on the type of soil you use.
Yes. So blue or lavender, acidic soil, pH 5 to 5.5. Purple or violet, it is 5.6 to 6. Pink, red, alkaline, 6.5 to 7.5. So even soil pH can affect the color of the flower.
Right. Yeah.
You understand? So you can see the importance of pH in various dimensions. You understand?
Yeah.
And even in your curd, why it is stable? Because no other bacteria can grow at pH 4.6.
Oh, okay.
You can leave it out and it won't get spoiled. Whereas if you keep milk outside, it gets spoiled because the pH is 7.4. All organisms can grow. That is why our grandmothers learned that if you convert milk, you want to keep it, convert it into curd. It will be stable for another 2 to 3 days. You understand? So the pH plays a very important role in our daily life.
Okay.
Sometimes you can sit and write an article on pH and daily life.
Yeah.
You understand?
Yes.
So that it gives you an idea of how, it is so simply taught as pH, but its ramifications are tremendous.
It's in every part of our life.
And that you have to appreciate.
Yes.
Okay. So I gave you an idea of how important. You might find more examples also.
Okay.
And pH also causes corrosion. All these things are part of this thing.
Yes.
So you have to learn the importance.
Yes.
Have I convinced you enough today?
Yeah.
Okay. So I suggest you make your own notes, and next time we'll go through some specific problems. How to make a buffer and all that.
Okay.
Okay.
Yeah.
I hope today's was a fruitful exercise.
Yeah, it was. Yeah.
And today you were speaking more than I was. You were doing the homework, right?
Yeah.
So we'll stop over here and let me know when you want the next class so that.
Yeah, it'll probably be another Saturday or Sunday.
Okay, fine.
Okay then. Bye-bye.
Okay then, bye-bye.